Hello students. So our today's topic is magnetism and matter, NCERT section 5.2.3 to 5.2.4 and example 5.1 and 5.2. So let's begin with the topic. So this is disclaimer. The learning objectives from our today's lecture. So after this lecture you will be able to analyze the behavior of magnetic dipoles in uniform magnetic fields and compare it with electrostatic dipole systems to understand their similarities and differences in field interactions. So what are the topics that we are going to cover today is 5.2.3 section of NCERT, the dipole in a uniform magnetic field, example 5.1, NCERT section 5.2.4, the electrostatic analog, and example 5.2. So let's begin with the topic 5.2.3, the dipole in uniform magnetic field. So you can see the figure. A bar magnet, which is also known as dipole, magnetic dipole, is placed in a uniform magnetic field. Okay, so magnetic field is in the direction upwards. So north pole of this magnetic dipole or magnet will experience force in the direction of magnetic field. We have earlier drawn a analogous with the electrostatic also, that north pole is considered as positive charge. Okay, like in electric dipole, there is a positive charge. So similar to positive charge, there is north pole in the magnetic field. Okay, so it will considered similar to the positive charge, and south pole is considered similar or analogous to negative charge. Okay, so this magnet is placed in the magnetic field. This north pole will experience force in the direction of magnetic field, and south pole will experience force in the direction opposite to the magnetic field. Okay, so this dipole is making angle theta with the magnetic field, and direction of magnetic dipole moment is from south pole to north pole. Okay, so it is same as the direction of magnetic field lines inside the magnetic bar. Okay, so inside the bar magnetic field lines are from south to north, and hence magnetic dipole moment is having same direction for a bar magnet, or for a dipole it is from south to north pole. Okay, so you can see in the diagram. Now we will see, consider a bar magnet with pole strength, so that Qm is pole strength. We took charges Q and minus Q in the electric dipole moment, and in the magnetic dipole moment we will take Qm as the pole strength. Okay, so what was the charge, what was the electrostatic force? F equal to Q into electric field. In this chapter, the magnetic force we will consider pole strength into magnetic field. Okay, we are drawing analogous to the electrostatics. So that's why in place of charge we are taking pole strength, in place of electric field we are taking magnetic field. So consider a bar magnet with pole strength Qm, length 2L, and magnetic moment, which is represented by M, equal to Qm into 2L, placed in uniform magnetic field B vector as shown in figure above. Okay, you can see in the figure also, I have also explained the figure. So forces, taking analogy with the electric forces on a charge QE. Okay, so I have also mentioned that electrostatic forces represented by F equal to QE into electric field. Similarly, taking analogy, we can explain that forces on the poles is Qm into B. Okay, so north pole experiences a force Fn that is represented by Qm into B, and south pole will experience force minus Qm into B. Okay, both forces are equal in magnitude. Now you can see it is similar derivation that we have done in electrostatics also. Okay, so if you remember that derivation, it is very easy for you. Okay, otherwise you can also do it if you are attending the daily lectures. So both forces are equal in magnitude. Okay, you can see both forces are equal, and exactly opposite in direction. Okay, so they will get cancelled out. So net force on the magnet, net force on this bar magnet will be 0. But because the line of action, what is line of action? This, the line along which this force is acting, this, and line along which this dotted line, this QMB is acting. So these line of action are not same for both forces. There is some perpendicular distance, that SP, that is some perpendicular distance existing between two lines of action. Okay, so net force is 0. Net force is 0. F net is equal to Fn plus Fs, which is QMB plus minus QMB, which is equal to 0. Hence, there is no translation motion. Since net force is 0, that means there is no translation motion of the bar magnet. But net torque is not 0 in this case. Okay, because there is a perpendicular distance between the line of action of both the forces. They are not acting along the same line of action. Got it? So torque is there. So rotational motion of the bar magnet is there, but no translation motion. So torque. Now we will calculate torque. Both forces have different lines of action and hence produce a torque. So magnitude of this torque is given by tau is equal to perpendicular distance, this SP, and magnitude of the force. So what is the magnitude of force? Both forces are equal. So magnitude is QM into B. So tau will be, what is perpendicular distance? This is 2L. This is theta. Okay, if this is theta by geometry, you can find this is also theta. Okay, so you can find what is this distance. So this will be, okay, so this is theta. Okay, so by geometry, you can find this distance SP is 2L sine theta. Okay, by finding with the help of geometry, you can apply here. So it will result in 2L sine theta by using trigonometric ratios. Okay, into magnitude of force is QM into B. Okay, so it will result in QM into 2L B sine theta after rearranging. So this QM into 2L, what is this? Magnetic moment. Okay, it is similar to electric moment, electric dipole moment. What is electric dipole moment? Charge into separation between the two charges. That is electric dipole moment. What is magnetic dipole moment? Pole strength into separation between the two poles of the bar magnet. So QM into 2L B sine theta. So it will, tau will result as MB sine theta. Okay. Now in electrostatic, torque was Q E sine theta. Sorry, PE sine theta. What was P? Electric dipole moment. And what was E? Electric field. In magnetic field, P is replaced by M, magnetic moment, and electric field is replaced by magnetic field. Okay, so tau is equal to MB sine theta. And in vector form we can write M cross B. Okay, magnitude is MB sine theta. So in vector form, torque can be represented as M cross B, M vector cross B vector. Mark it as 5.2 equation. Okay, where M is magnetic dipole moment, B is magnetic field, and tau is torque. The dipole in a uniform magnetic field. Now we will calculate the potential energy. Okay, so the formula for magnetic potential energy can be calculated in a way that is very similar to how we find electric potential energy. Okay, in electrostatic chapter, so I have already mentioned in the beginning of the chapter that you have to draw all the analogous with the electrostatics or electric fields or with the electric dipole moment. Okay, so you should remember, you should revise that chapter also. Okay, so potential, we are going to find the potential energy of a magnetic dipole. Similarly, we found the electric potential energy of the electric dipole also. Okay, the formula for magnetic potential energy can be calculated in a way that is very similar to how we find electric potential energy. Okay, so this is the diagram. So this magnetic field is horizontal. So there is a magnetic needle placed in the magnetic field at some angle theta. Okay, so this is south pole, this is north pole. So figure 5.3b, magnetic needle in uniform magnetic field B. Work done by external force in rotating the dipole from theta 1 to theta 2. Okay, so we are going to rotate it. So we have to do the some work. Okay, so if we are rotating this magnetic needle against the magnetic field, so we have to do some work. Okay, that work is stored in the form of potential energy of this magnetic field. Okay, potential energy of this magnetic needle placed in the magnetic field. So work done by external force in rotating the dipole from theta 1 some angle theta 1 to another angle theta 2. Okay, we are rotating it through some theta 1 angle to theta 2 angle. So this work done is stored in the form of potential energy. So work done will be equal to T into d theta. Small work done. This is small work done. So in rotational motion, you may have studied that what is work done? Torque into angular displacement. Similarly, in the translational motion, force into displacement. And in rotational motion, torque into angular displacement. So tau into theta. So this tau into d theta is very small displacement. So this is small work done. Tau d theta is small work done. Okay, so small work done, we are integrating this small work done from theta 1, from angle theta 1 to theta 2, because we are rotating this magnetic needle from theta 1 to theta 2. Okay, so work done is equal to theta 1 to theta 2. What is tau? We have calculated mb sine theta in the previous slide. Okay, put this value, now integrate. Okay, so work will be equal to mb minus cos theta. Okay, and limits tends from theta 1 to theta 2. So integration mb is constant, it will come out of the integration. So integration of sine theta is minus cos theta. Okay, integration of cos theta is sine theta. Integration of sine theta will be minus cos theta. So it will result in minus cos theta, theta 1 to theta 2. Okay, so after putting theta limits, it will result in minus cos theta 2 plus cos theta 1. So after rearranging, it will become mb cos theta 1 minus cos theta 2. Got it? Now to define the potential energy, we have to define the reference also. Okay, so we will also fix the reference point. So taking the reference position at theta 1 equal to 90 degree. When we take theta equal to 90 degree, it means cos theta will be 0. That means potential energy at that point will be 0. Okay, so if we multiply mb with cos theta 1 and cos theta 2, it will result in mb cos theta 1 minus mb cos theta 2. These are two expressions for potential energy at different orientations, at different angular displacements. Okay, so we are taking reference when theta 1 is equal to 90 degree. At this theta 1, cos theta 1 will become cos 90 degrees 0. So cos theta 1 becomes 0. So potential energy will become 0 at the theta 1 orientation. That means potential energy of this needle will be 0 when this needle makes 90 degree angle with this magnetic field. Okay, when this needle will make 90 degree angle with this magnetic field, potential energy of the this needle will be 0. So we will take it as reference. 0 potential energy, take it as reference. So taking the reference point at theta 1 equal to 90 degree, where u is equal to 0, the potential energy at an angle theta 2 equal to theta. Now we will theta 1 we have put 90 degree, so we will put theta 2 as only theta. We have eliminated the theta 1, so we will put theta 2 as theta. So expression will come out to be, so u theta will be equal to minus mb cos theta. Okay, so this mb cos theta, it is the result of dot product of two vectors. So it will result in minus m dot b. Okay, it is similar to the potential energy of electric dipole, which was minus p dot e. Okay, here minus m dot b. Okay, so this is the potential energy to rotate a magnetic needle through angle theta. Okay, so um magnetic potential energy will be equal to minus m dot. So where m is magnetic dipole moment, b is magnetic field, and um is potential energy. The dipole in a uniform magnetic field. Figure showing different orientations of bar magnet with respect to magnetic field. Okay, so these are some cases, some special cases of this derivation we have done. Okay, so we will see these special cases when magnetic dipole moment is aligned in the direction of magnetic field. This is conclusion as well as special cases. Okay, conclusion from the whole topic that we have done today and yesterday. Okay, so when this magnetic bar is placed in such a way that magnetic moment is in the direction of magnetic field, that is, magnetic moment is from south to north, it means magnetic moment is parallel to this magnetic field. Okay, then theta will be 0 because it is parallel. When theta is 0, tau will be mb sin theta. Sin 0 will be 0, so torque will be 0 also, and it is the condition of minimum torque. Okay, so you question can be asked, question should be in the form that at what orientation torque of the bar magnet, torque on the bar magnet will be 0. Okay, so at theta equal to 0 when magnetic moment is parallel to the magnetic field. So at this orientation, u is equal to u minimum because mb cos theta, cos 0 is 1. Okay, so minus mb, potential energy, magnetic potential energy of this bar magnet will be stored in this bar magnet will be minus mb. Okay, so this is the minimum potential energy of this bar magnet, which is stable position, also known as stable equilibrium. Got it? So a stable equilibrium is at theta equal to 0. Now, when this magnetic when this bar magnet is placed perpendicular to this magnetic field, such that magnetic moment is having angle 90 degree with this magnetic field. Okay, so theta is now pi by 2, so tau will be equal to tau max because mb sin theta, sin 90 will be 1. So this is the maximum value of the torque which is acting on this bar magnet, so which is mb, and u will be equal to 0 because cos 90 is 0, so u is 0 here. We also took reference. This is the reference condition for potential energy derivation. Got it? Now, when this bar magnet is placed anti-parallel to this magnetic field, okay, so when magnetic moment is having direction opposite to this magnetic field, and angle between both these vectors will be 180 degree. So theta is pi, okay, which is 180 degree. So torque is again mb sin theta, sin 180 degree is 0. So torque again is minimum. Okay, torque is minimum at two orientation, when it is bar magnet is parallel or anti-parallel to the, when magnetic moment is parallel or anti-parallel to the magnetic field. So torque will be torque minimum equal to 0. But potential energy here will not be minimum. Potential energy here will be maximum because minus mb cos theta. So theta is 180 degree. So cos 180 degree is minus 1. So minus is already in the formula. So again 1 minus. So it will become positive mb, which is maximum potential energy. Okay, so this is also equilibrium position, but what equilibrium? Unstable position, unstable equilibrium. Got it? So at theta equal to 180 degree, there will be unstable equilibrium and potential energy will be maximum, torque will be minimum. Okay, again, this is the magnetic dipole in magnetic field. This is the conclusion of the whole topic. From the relation of potential energy of magnetic dipole moment at theta equal to 0 degree, potential energy is minimum, that is most stable position given by minus mb, and at theta equal to 180 degree, potential energy is maximum, which is most unstable position given by mb. So example 5.1. What happens if a bar magnet is cut into two pieces? Transverse to its length. Transverse means perpendicular to its length, and from midway, and second is along its length. Okay, so what happens? These are the two cases. This is the A part of this 5.1 example. There are 4 total parts. So we will do part by part. So this is the A part. What happens? Okay, so let's see the solution. In either case, one gets 2 magnets each with the north and south pole. Got it? So we have also discussed that monopoles do not exist. Okay, if we cut the magnet, it will result in the 2 magnets having their own north and south pole, but only magnetic strength will decrease. Got it? So in either case, one gets 2 magnets each with the north and south pole, but strength of magnetic moment will become half as magnetic moment is given by pole strength. Multiplied magnetic moment is given by pole strength into distance between the 2 poles. Okay, so by this expression, M equal to Qm into 2L. In both cases, if we cut a magnet transverse to its length, so length will become half, so magnetic moment will decrease, which means magnetic strength will become half. If we cut it along length, then pole strength will decrease, pole strength become half. Eventually, magnetic moment will decrease and magnetic strength will also decrease. When cut transverse to its length, then length of the bar magnet becomes half. So the magnetic moment also becomes half. Okay, like this. You can see in the diagram. Okay, so magnetic moment becomes half. That means magnetic strength of these 2 resulting magnets will be half of the initial magnet. When cut along the length, the pole strength becomes half. Now, if we cut the magnet along the length will remain same for both the magnets. Resulting magnets length will be 2L, but pole strength will be Qm by 2. Okay, in both cases, magnetic moment will become half, due to which magnetic strength will decrease. So due to which magnetic moment becomes half, like this. If we cut along the length, it will result in 2 magnets and this magnetic moment will become half. Okay, M by 2. Okay, pole strength also decreases. Pole strength will become half, magnetic moment become half, M by 2, M by 2. Okay, length will remain same, 2L. B part. A magnetized needle in a uniform magnetic field experiences a torque, but no net force. This derivation we have discussed, that when we place magnetized needle or any bar magnet, okay, these are similar terms, in a uniform magnetic field, it experiences torque but no net force. Okay, but an iron nail near a bar magnet, however, experiences a force of attraction in addition to a torque. Okay, you may have seen that when we place a iron nail near the magnet, okay, why it is not experiences only torque, it is experiences force only, it will attract towards the magnet. Okay, so why iron nail is experiences both torque and force? It will rotate. When it come towards the magnet, it will change its orientation, but it is very fast, you cannot detect it. Okay, also it will experience force, due to which it will attract towards the magnet. Okay, so why? We will see the reason. So there is equal and opposite force on each pole of the magnetized needle. Okay, firstly we will discuss about magnetized needle. So there is equal and opposite force on each pole. We have discussed in the derivation also on the magnetized needle or magnetic bar. Okay, when placed in a uniform field, hence force on each pole get cancelled out and net force on the magnetized needle is 0. Okay, now due to field produced by bar magnet, iron nails get magnetized and then there is induced magnetic moment in the iron nail. Okay, so when iron nail is placed near the bar magnet, okay, so it will get magnetized and induce the magnetic moment. Okay, like we induce the charges. If we place any uncharged material, uncharged conductor or any uncharged material near the charged material, it will induce the charges in the uncharged material. Okay, like hair comb example. Okay, when we rub the comb in the hair, okay, it will get charged. So paper, small pieces of paper is uncharged. we place this comb near the uncharged paper pieces. So paper pieces also induce the charges and get attracted towards the comb. Similarly, when we place an iron nail near the bar magnet, it get magnetized and induce the magnetic moment. It will induce the magnetic properties. Okay, so what is this magnetization or how it is getting magnetized? We will discuss it detail in this chapter only in the later topics. Okay, but magnetic field, now this is the main point of this crux of the matter here. Okay, so what magnetic field of a bar magnet is not uniform. Okay, but magnetic field of we place the magnetic needle in the uniform magnetic field, that's why net force on it is 0. But we place the iron nail near the bar magnet and magnetic field due to bar magnet is not uniform. Okay, due to this non-uniform magnetic field, iron bar experiences different force on its induced poles. Okay, so the part of the iron nail which is placed near to the end of the iron nail which is placed near to the bar magnet will experience more force than the end that is away from the bar magnet. So both the poles that are induced due to the magnetization of the iron nail, so both poles will experience different forces on its induced poles. Okay, and hence net force is not 0. Net force on the iron nail is not 0. Therefore, it experiences both net force and torque also. The net force is attractive because induced south pole, say, in the iron nail is closer to the north pole of magnet than that of the induced north pole in the nail bar. Okay, we can also say that induced south pole is closer or induced north pole is closer. Either of the pole is closer to the bar magnet. Okay, so we can fix one pole. Okay, we say south pole. Okay, so net force is attractive because I have also already mentioned that the end which is near to the bar magnet will experience more force. Okay, so net force will be attractive. So the net force is attractive because induced south pole, say in the iron nail, is closer to the north pole of the magnet than that of the induced north pole in the nail bar. So it will attract the nail bar, iron nail. Okay, and also both net force and torque is acting. Okay, understood? C part. Must every magnetic configuration have a north pole or a south pole? Okay, we have discussed that monopoles do not exist. But can it be that both poles do not exist? There is no north pole or south pole for a configuration. Okay. What about the field due to a toroid? Okay. So toroid we have not discussed in detail in the previous chapter, but toroid is the form of when we hold the ends of the solenoid and after bending the solenoid we will touch the two ends of the solenoid and making a circular configuration. That circular configuration is called toroid. Okay, so solution: no, it is not necessarily true always that every magnetic configuration have a north pole and a south pole. Why? It is true, this condition that every configuration have north pole and south pole is true only if the source of the field has a net non-zero magnetic moment. If any configuration is not having non-zero magnetic moment, then it will not have north pole and south pole. Okay, the only condition for having north pole and south pole is true only if the source of the field has a non-zero net magnetic moment. Okay, so examples of this condition is, this is not true for a toroid or even a straight infinite conductor. Okay, for a toroid, because we have we hold the ends of the solenoid. Okay, both ends. One end of the solenoid is north and one end of the solenoid is south. We have bent the solenoid in the form of circle in the circular configuration and touched both the ends of the solenoid at one point. So now there is no pole of the resulting configuration, which is toroid. Okay, so there is no north pole, no south pole. Similarly, for a straight infinite conductor, we don't know where the ends are because it is infinite conductor, so we cannot determine the ends. So if there is no end of the straight conductor, there is no pole. Okay, only magnetic field is in the direction of concentric circles, but we cannot determine the ends. Okay, so no net there is their net magnetic moment is 0. So there is no north pole and south pole for special configurations like straight infinite conductor and toroid. So D part. Two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. We do not know which one. Okay, so there are two identical bars A and B, one of which is definitely known to be magnetized, but it is not definite that other is magnetized or not. It can happen that both are magnetized, or it can happen that only one is magnetized. Okay, but we know that one is definitely magnetized. We don't know about other. How would one ascertain? Ascertain means find out. How would one find out whether or not both are magnetized? Okay, how will you find that whether one is magnetized or both are magnetized? This is the first part of the question. Or other part of the question, if only one is magnetized, now we have fixed that only one is magnetized. Okay, how would one ascertain which one? Now how will you find out that which one is magnetized? Use nothing else but the bars A and B. Okay, firstly we will do the first part, that where one of the bar is definitely magnetized. We have to find that other is magnetized or not. Okay, so let's see the solution. We can use fact that both like poles of the magnet bar repel and unlike poles attract. Try to bring different ends of the bar closer. Okay, try to bring the different ends of A and B bar together. Okay, a repulsive force in one of the situation will indicate that both are magnetized. If there is only one magnetized bar and other is not magnetized. Okay, when we place this unmagnetized bar near the magnetized bar, it will induce the magnetization in the unmagnetized bar. Okay, so it will attract that bar only, like the iron nail. There will be no repulsion, only attraction. Okay, from that thing we can consider that there is no any case of the when we bring different ends of the bar, there is no any case when both bars are repelling. That means one is magnetized, other is unmagnetized. Okay, but if there is a repulsive force, if there is a case, one situation when there is a repulsive force between the two magnetized, there is two bar magnets A and B, this will indicate that both are magnetized. Okay, and we have brought similar or like poles together. Okay, unmagnetized means simple iron bar which is having no magnetic properties. Okay, if force between two bars is always attractive, if there is one magnetized bar, there is one only iron bar, no magnetization is there. Okay, so it will attract the magnet on the magnet will attract the iron bar only, it cannot repel it. Repulsion case is only when other magnet is also having magnetization. Okay, other magnet is also having north south pole. Got it? So if force between two bars is always attractive, then one of them is not magnetized. So first part is finished. Now move on to the second part. What is second part? One is magnetized, only one is magnetized, so we have to find which one. So in a bar magnet, the intensity of the magnetic field is the strongest at the two ends and weakest at the central region. That we also know. Okay, this fact may be used to determine whether A or B is the magnet. In this case, pick a one. Say A. We are picking up one magnet. Say A means we have picked up A bar and lower one of its end, and we have lower one of its end. Firstly, on the we are bringing its one end near the. Firstly, we are bringing its end of the A bar. We are bringing end of the A bar firstly near one of the ends of the other, that is B. Okay, we are bringing one end of the A bar near the end of other bar B. Okay, and secondly, after then on the middle of the B. Okay, we will do it in two parts, two steps. We will bring the one end of A firstly near the one end of B, and secondly near the middle of the B. Okay, now we will observe, if you notice that in the middle of B, A experiences no force or weak force, then B is magnetized. Okay, if there is no force or weak force, then it means that B is magnetized. And if you do not notice any change in the magnitude of force from the end to the middle of B, then A is magnetized. Okay, so if the force is same throughout the B magnet, if you are lowering the one end of the A magnet and bringing it towards the end of B and at the middle of the B, if there is no change of the force at both cases, then it means A is magnetized. Why A is magnetized? Because A is inducing the magnetic field in the B. A is inducing the magnetic moment in B. So force of attraction will be same at the ends and at the middle also. Okay, but if B is magnetized, due to the magnetic field lines of the B, magnetic field will be strong at the ends and weak or almost zero at the middle. So when we bring the one end of A at the end of the B, then it will experience more force. And when we bring the one end of A bar near the middle of the B, it will experience weak force or no force. Then it means B is magnetized. Got it? So next part, which is 5.2.4, the electrostatic analog. Now we will draw the analogies, some analogies. So we studied expression for the magnitude of electric field at far axial point of an electric dipole, that we have discussed in the yesterday's lecture in chapter electric charges and field, and it was given by. So what was the magnetic axial electric field due to a short dipole at far axial point? E axial is equal to 2p upon 4 pi epsilon naught r cube. Expression for torque on electric dipoles was TE tau E is equal to P vector cross E vector. And similarly, expression for potential energy of electric dipole was in the chapter electric charges and fields, UE, electrostatic potential energy, is given by minus P vector dot E vector. Now similarly for magnetic field, these three formula will be. So now in this chapter, magnetism and matter, we saw that expression for magnitude of magnetic field at axial point of the magnetic dipole is BA, which is equal to mu naught 2m upon 4 pi r cube. Okay, we have replaced E with B, replaced P with M. Okay, so mark it as 5. This was 5.1 equation. Okay, so expression for torque on magnetic dipole moment was tau m equal to m cross m vector cross b vector. Mark it as 5.2. And similarly, expression for potential energy of magnetic dipole was um equal to minus m vector dot b vector. Okay, so in electrostatic it was ue equal to minus p vector dot e vector. Okay, now comparison of equation 5.1, 5.2 and 5.3 suggests that magnetic field at large distances due to bar magnet of magnetic moment m can be obtained from the equation for electric field due to an electric dipole of dipole moment P by making the following replacement. So by making the replacements in the formula for electric field for electric dipoles, we can find the formula for magnetic field at a large distance due to a bar magnet of magnetic moment N. So E, we should replace E with B, P with M, and 1 by epsilon naught with mu naught. Okay, using these replacements and from expression of electric field of electric dipole moment at equatorial line. Now for equatorial line, we have already discussed in our previous class that for equatorial line, what was electric field due to electric dipole? E equatorial is equal to minus P upon 4 pi epsilon naught r cube. Similarly, we can do the replacements and we can write down the equatorial field, equatorial magnetic field BE of a bar magnet at a distance r, where r is much greater than the length of the bar magnet, where L is the length of the magnet, or we can say magnetic dipole. Okay, so this distance we have to find the magnetic field at a very large distance as compared to the length of the magnet at equatorial point, or we can say equatorial line. What is equatorial line? The line perpendicular to the magnetic moment and passing through center of the bar magnet. So BE will be equal to, by making suitable replacement, we can write minus mu naught M upon 4 pi r cube. Mark it as 5.4 equation. And likewise axial field BA as derived earlier also of bar magnet for r much greater than L will be BA equal to mu naught 2M upon 4 pi r cube, which is 5.5 equation. Okay, so there is a table, the dipole analogy. It is conclusion of this topic. So this table is representing the analogous from electrostatic to magnetism. Okay, so we have to replace 1 by epsilon naught with mu naught. For dipole moment, electrostatic electric dipole moment is P. In magnetism, magnetic dipole moment is M. Okay, so you should remember this table. This is the conclusion of whole topic. So equatorial field for a short dipole, or we can say at a large distance. So minus P upon 4 pi epsilon naught r cube is for electrostatic, and minus mu naught M upon 4 pi r cube is for magnetism in the magnetism chapter. Okay, so axial field for a short dipole or for a very far axial plane. Okay, these two things mean same. These two things meant same for a short dipole, or we can say at a far axial point. For a short dipole, or we can say for a far equatorial point. Okay, these two things are same. So 2p magnetic field is 2p upon 4 pi epsilon naught r cube, or in magnetism, magnetic field is mu naught 2m upon 4 pi r cube. So when magnetic needle or bar is placed in external field, then torque will be P vector cross E vector, and in magnetism torque will be M vector cross B vector. When magnetic needle or bar or dipole moment, electric dipole is placed in external field, then the electrostatic potential energy or magnetic potential energy will be, so electrostatic potential energy will be minus P vector dot E vector, and in magnetism that magnetic potential energy will be minus M vector dot P vector. So this is the table for whole topic. Now example 5.1, 5.2. Figure 5.4 shows a small magnetized needle P placed at a point O. The arrow shows the direction of its magnetic moment. Okay, the direction of arrow showing its direction of magnetic moment. The other arrows show different positions and orientation of the magnetic moment of identical magnetized needles Q. Okay, so this is the diagram. Okay, so there is a small needle P, okay, placed at O point. So the direction of this arrow is showing the magnetic moment of this magnetic needle. There are other small magnetized needles are given Q1, Q2, okay, Q3, Q4, Q5 and Q6. Okay, so the direction of the arrows are giving the direction of magnetic moments and their orientations. Okay, so this is the diagram. What we have to find, the A part, in which configuration the system is not in equilibrium. Configuration means configuration of this P with different other needles like PQ1, configuration PQ1. In configuration PQ1, it is P and Q1. In configuration PQ6, it means we have to analyze only P and Q6 and neglecting or ignoring the other needles. Okay, so in what configuration the system is not in equilibrium is the A part. B part is in which configuration is the system in first stable and second unstable equilibrium. And third, C part is which configuration corresponds to the lowest potential energy among all the configurations shown. So we'll do it part by part. Okay, first solution, we learned that magnetic potential energy of magnetic dipole arises in presence of magnetic field. Okay, so if there is a magnetic field, then only there will be potential energy stored in the magnetic dipole. If magnetic field is zero, then there is no magnetic potential energy. It is clear of a magnetic dipole. In this example also, potential energy of the configuration arises due to potential energy of one dipole, say Q, in the magnetic field of P. So here, in this example, that P needle is the primary needle. Okay, so it is producing the magnetic field and other needles are affecting by this magnetic field. We have to see the potential energy of other magnetized needles in the presence of magnetic field produced by the P. Okay, we have to find the potential energy of Q1, Q2, Q3, Q4, Q5, Q6 in the presence of magnetic field produced by the P needle. Okay, got it? So using the result for the field due to P is given by the expression equation 4.5, 5.4 and 5.5. So the magnetic field expression, magnetic field produced by the P needle is given by BP equal to minus mu naught MP upon 4 pi r cube. This is for the normal bisector when the magnetic field is perpendicular to magnetic dipole moment. Okay, when magnetic field is perpendicular to the magnetic dipole moment of Q. This is the formula for magnetic field in that condition on the equatorial plane. Got it? And on the axis, the above expression is for the on the normal bisector. Okay, magnetic field at the normal bisector is given by this, and magnetic field on the axis of this P, along this P, along this magnetic dipole moment is given by BP is equal to mu naught 2 MP upon 4 pi r cube is the magnetic field for the on the axis. Okay, so where MP is the magnetic moment of the dipole P. Equilibrium is stable. Now you can see this is important point. Equilibrium is stable when MQ is the magnetic dipole moment of the other magnetized needles, that is Q1, Q2, Q3. So we have generalized it with Q only. Okay, so equilibrium is stable when magnetic dipole moment of other magnetized needle, that is given by MQ, is parallel to the magnetic field produced by B. And equilibrium is unstable when magnetic moment of other needles is anti-parallel to the magnetic field produced by the P needle. Got it? So A part. Firstly, we will do A part. So this is the diagram. Let's see the solution. Consider the arrangement of PQ1 and PQ2. Okay, in this diagram, arrangement PQ1 and PQ2. Okay, separately. Now, at the locations of Q1 and Q2, you can see at the location magnetic field produced by this P1 along this is along axis will be axial field, and along this, because the magnetic field will be magnetic field at equatorial line perpendicular to this P will be perpendicular to these Q1 and Q2. Okay, magnetic field produced by P at the locations of this Q1 and Q2 will be perpendicular to the magnetic moment of this Q1 and Q2. So it will not be in equilibrium state. Okay, so at locations of Q1 and Q2, magnetic field due to P, that is BP, is perpendicular to both MQ1 and MQ2. What is MQ1? Magnetic moment of Q1 needle and magnetic moment of Q2 needle. That arrow is showing the direction of magnetic moments. Okay, so magnetic field produced by this P will be perpendicular to both MQ1 and MQ2. Okay, hence PQ1 and PQ2 configuration is non-equilibrium. So these both configuration are non-equilibrium because the angle between the magnetic moment and magnetic field is 90 degree. Okay, which means U will be 0 and that is non-equilibrium condition. So in which configuration is the system stable and second one is unstable? So we'll do first part first. So first part, consider the arrangement PQ3 and PQ6. These arrangement PQ3 and this PQ6. In both conditions, for Q6, you can see for Q6, the magnetic field, axial magnetic field due to this P will be in same direction as magnetic moment of Q6, and equatorial, and this Q3 is on the equatorial line for this magnetic needle P. So magnetic field, equatorial magnetic field will be, equatorial magnetic field due to this P will be at this Q3 will be opposite in the direction to the magnetic moment of P, which means in the direction of this Q3. Okay, that means magnetic field is parallel to this Q3 and also parallel to this Q6. Okay, you can also draw the magnetic field lines for simplicity, or you can see you can have strong foundation of equatorial field and axial field. We know that axial field of any magnetic needle is having direction same as the magnetic moment. Okay, so at this axial line, magnetic field will be in the direction same as the magnetic moment of this P. But at equatorial line, means at location Q3 and Q5, magnetic field will be having direction opposite to the magnetic dipole moment of this P, means in the downward direction. That is clear? So consider the arrangement of PQ3 and PQ5, 6. At the location of Q3 and Q6, magnetic field due to P, that is BP, is parallel to both MQ3 and MQ6. Okay, magnetic dipole moments of Q3 and Q6. Hence PQ3 and PQ6 configuration is stable equilibrium. Okay, so they are parallel, so angle will be 0 degree, so potential energy will be minimum. Okay, so this is stable equilibrium. Now its second part, for unstable equilibrium. So consider the arrangement PQ4 and PQ5. Okay, for PQ4 and PQ5, I have discussed magnetic field due to this P at this equatorial line will be opposite to the direction of this magnetic moment of this P, means in the downward direction. Okay, so magnetic field at the location of Q5 is opposite to the magnetic moment of this MQ5, means they are anti-parallel. Also axial field is in direction same as the magnetic moment, so it is in the upward direction, but Q4 is in the downward direction. So magnetic moment of this Q4 is anti-parallel to the magnetic field produced by P. Okay, so at locations of Q4 and Q5, magnetic field due to P, that is BP, is anti-parallel to both MQ4 and MQ5. That means PQ4 and PQ5 configuration is unstable equilibrium. Got it? Angle is 180 degree. That means potential energy is maximum MB. C part. Which configuration corresponds to the lowest potential energy among all the configurations shown? Okay, so you have to determine the lowest potential energy among all the configurations. So let's see the solution. Magnetic field due to magnetic dipole moment at axial is double. So we seen that magnetic field at axial point, magnitude of magnetic field at axial point is double to that on the equatorial position for same distance, because there is 2 in the numerator for axial magnetic field. Now PQ3 and PQ6 both are stable equilibrium, means potential energy is negative or minimum for both the conditions. Okay, but Q3 is on equatorial location and Q6 is on axial location. So magnetic field for Q6 will be more. That means potential energy for Q6 location will be more. So potential energy is more negative for PQ6 configuration, as magnetic field is higher at the axial position. So Q6 is along the axial line of this P needle. Hence PQ6 configuration corresponds to the lowest potential energy among all the shown configurations. Okay, so there is a summary. When a bar magnet of dipole moment M is placed in a uniform magnetic field B, force on it is 0, torque on it is M cross B, and its potential energy is minus M dot B, where we choose the 0 of energy at the orientation when M is perpendicular to B. There are some practice questions you have to practice yourself. What is the torque on a magnetic dipole when it makes 30-degree angle with 2 Tesla magnetic field? Given magnetic moment is 4 ampere meter square. Find the potential energy of magnetic dipole in a 1.5 Tesla field when aligned. Given magnetic moment is equal to 2 ampere meter square, and when aligned parallel to field and B part anti-parallel to field. Means theta is 0 degree and second is 180 degree. So third question, calculate the maximum torque possible on a dipole with moment 3 ampere meter square in 4 Tesla field. Maximum torque is when theta is equal to 90 degree. Okay. So thank you, but we have to do the DPP section. Okay. So magnetic dipole of moment M placed in a uniform magnetic field B, the torque acting on the dipole is given by So I am marking randomly now due to the time shortage. An iron nail is placed near a bar magnet. The nail experiences both we have discussed it. Yes. Both a torque and a net attractive force. 2 identical iron bars A and B are given where only one is magnetized. Okay, we have also done it in the example. In the exercise, example also. To identify the magnetized bar without external tools, you should observe which bar attracts iron fillings more strongly, bring a different end of the A close to and check the repulsion, heat both, place both bars perpendicular to each other and measure the force. Okay, so I am marking randomly here. The magnetic potential energy of a dipole in a uniform magnetic field is minimum when angle between M and B is. So magnetic potential energy is minimum when angle is a bar magnet is cut transversely into 2 halves. Which of the following statement is correct? Each half has only a north pole, each half has a south pole, and each half is a magnet with both north and south poles. Okay, the 2 halves lose their magnetic properties. Okay, so that question is a confusion. Okay, bring different ends of A and B and check for repulsions. But this is for the first one, when one is definitely magnetized and we don't know about other. Okay, so it is not written clearly, but second one is more appropriate option among all. Okay, so thank you. I hope you enjoyed the session.